Todd Dunn here for Life on the Edge. Today's video is about installing solar power on an RV. This is part 1 of 2. In this part, I'm going to be talking about how to decide just how much solar power you need if you want to stay off the grid for a little while, and some of the basics of the electrical calculations that are involved, and finally a little bit about choosing solar power controller. The first question that I want to look at today is how much solar power do you need on your RV to live off the grid? Well, it depends. What does it depend on? It depends on where you're going to use your RV. How are your solar panels mounted? How much power do you use in a day from your batteries? And finally, to a lesser extent, what is your battery capacity? One of the biggest factors in deciding how much solar power you need for your RV is location. Where are you going to use your RV? And when are you going to use it? I'm going to address this from the perspective of someone who might be full-timing in their RV and is going to use the RV year-round but in different locations. Let's consider that you go down south in the winter to Arizona, Florida, Texas, Southern California, someplace like that. Well, what are the conditions down there in the winter? First off, what time frame do we need to look at? Well, I would say that initially we're going to look at the shortest days when we're going to get the least solar power. That's going to be the limiting factor in deciding the size of our solar array for use down south in the winter. Okay, how much sun is there? Well, insolation, say in Arizona, is about 3 kilowatts per square meter. That's just an indication. That's plenty to give you full output from your panel at peak solar hours around noon. The next consideration is just how many hours of sunlight do you have each day? Well, in Arizona, for example, or Texas, you might have about 9.5 hours of sunlight a day during which your solar array can generate electricity. How much of the time is it sunny is another consideration. Arizona, again, maybe 75% of the time. What about in the summer? Probably not going to stay down south where it gets hot and dry out west, or hot and humid if you're back east. So you go up north. So that means that maybe you're going to be up north from May through September. Your shortest days are in May and September, so those are the days that we will use to characterize our solar array for up north. At that time of year, the solar intensity is about 4 kilowatts per square meter, so that's a little better than down south in the winter. Not a lot, but say comparable. The big difference is the number of hours of sunlight in a day. It's up to 14.5, say in Washington State, Montana, Minnesota, or northern Maine. However, in those parts of the world, it's less sunny than it is, say, in Arizona or Texas. We can combine these various numbers into a factor of sorts. This is my personal factor, it's nothing official, that tells you approximately how much solar power you're going to get, at least in terms of relative calculations. For my southern example, which is Arizona, the number works out to be 21.5. For my northern example, which I used Washington State for, it works out to be 35. So you get almost twice as much solar power in Washington in the summer as you do in Arizona in the winter. That means that if you're going to be traveling, you should use our winter calculation for Arizona to determine the size of your solar array, because that array will certainly be adequate up north in the summer. Another big consideration is how are your panels mounted? The first consideration is, do you want to mount them permanently on the roof of your RV, or do you want them to be portable on the end of a cable so that you can set them up away from the RV? Why would you want to make them portable? Well, there are a couple possibilities. One is you like to park your RV in the shade to keep it cool inside. Solar panels don't work well in the shade, so if they're portable, you have the option of parking in the shade under a tree, for example, and then maybe setting the solar panels up away from the RV so that they're in direct sunlight. Another consideration is convenience. Do you want the convenience of having the panels permanently mounted so you can basically forget about them? Or do you want them portable, which is a bit more of a hassle because you have to set them up every day, take them down? What about exposure time? If they're on the roof permanently mounted, they're there at first light and they're there at sunset. They're getting exposed to the sun all day. If they're portable, well, you have to get up in the morning and set them out. You also have to, if you feel that there's reason to take them down in the evening and put them away. Furthermore, another consideration for roof mounted is that if your panels are roof mounted, they're going to be collecting solar energy while you're driving, which is a big positive, that they're going to be charging your batteries even when you're on the road. Okay, another consideration is, do you want to mount the panels horizontally, or do you want to tilt them so that they face the sun? If you mount them horizontally, either in a permanent mount on your roof or in a portable mount just by laying them flat on the ground, you can pretty much forget about them. You don't have to aim them at the sun or anything, just make sure they're in the sun. But you will lose about 15% of output relative to tilting the panels so that they face the sun. However, if you've got them on the roof and set up so that you can tilt them, you have to climb up there, tilt the panels. You also have to orient the RV so that they face the sun. That may not always be possible. If they're portable, it's a little easier. You can just set up some legs on the panels to tilt them to face the sun. That will make them susceptible to blowing over if there's any wind and possibly being damaged. At any rate, the decision of how to mount your panels really comes down to personal preference, and does that last little 15% of output matter that much to you? Now let's look at how much power do you use. I'm going to spend a little bit more time on this because it's a little bit more involved. What uses power? And here we're talking about power coming from the batteries, either directly in DC circuits or via an inverter to run AC appliances. Well, what uses power? What about your refrigerator? Well, your refrigerator runs on propane when you're not plugged in. Well, not really. Its control electronics run off of your battery, and they run all the time. So if your refrigerator is connected up and turned on all day, they're going to run 24 hours. That can add up. Heat. Well, if you've got a heater in your RV, the blower is a big draw for power. Also, the heater has control electronics, a propane solenoid, etc., that's going to draw power all the time that the heater is on. Same applies to your water heater. It has control electronics and a propane solenoid that whenever you turn it on to heat water, it's going to be using electrical power. Then there's electronics. Do you have a TV that runs off your battery? What about a computer? Anybody on YouTube has a computer that they're using that's probably going to be plugged in either just to recharge the battery or plugged in continuously while you're using it. You have a phone, you're going to have to recharge it. You have an internet hotspot, got to charge that up unless it runs off AAA batteries or something. There are a lot of different electronic things that you might be running, a radio, for example. One consideration with electronics, particularly things like a TV, is that that TV, if it has a remote, is on all the time. Even when you have it turned off, there's circuitry running to detect when you push the on button with the remote. So you might want to disconnect the TV from the DC circuits by throwing a circuit breaker to avoid that parasitic draw, which can add up over time. Then there are miscellaneous other things that you might have. You might have a hair dryer. You might have an electric razor that you either recharge or plug in. You might have a coffee maker that you use occasionally. Then there's the microwave that you might use. All of these can be potentially big power draws, and they all have to be considering and determining how much power are you drawing from your batteries. Now let's look at a little bit of the arithmetic and electrical theory that you really need to know something about in order to understand how to size a solar array. Some terminology first. Electricity is thought of in terms of volts, which is called electromotive force, basically how hard the electricity is being pushed through the wires. Amps, which gives the symbol I, which is how much electricity is being pushed through the wire, and power in watts, which is the product of volts times amps. How hard you're pushing, how much you're pushing. That determines power. If you're using 1 amp for a period of an hour, we call that 1 amp hour, which is abbreviated amp-HR for hour, or simply AH. If you use a power of 1 watt for 1 hour, that is 1 watt hour, which is abbreviated WH. You've probably seen that more commonly on your home electric bill as kilowatt hours. A kilowatt is 1,000 watts. Again, power is equal to volts times amps. Why do you need to know this? Because we're going to be using it to figure out how much power individual components that are using power consume in our RV. Now, how are amp hours and watt hours related? It's pretty simple. Amp hours are just equal to watt hours divided by volts, and we'll be using that in a little bit. So, how do we figure out how much power an appliance uses? Well, everything has a label on it somewhere which describes how much power it consumes. I've put 3 examples here in this slide. The first is a laptop power supply. In the little green box, I've circled the area that tells you what the input power into the power supply is, and you want input power, not output power. In this case, it uses 1.2 amps at 115 volts. 115 volts is pretty typical for AC voltage. So this is an AC appliance. So using our power equals volts times amps, it comes out that this laptop consumes 138 watts when it's plugged in. So every hour that I use my laptop, I'm going to use 138 watt hours of power. Next thing, camera battery charger. Input voltage, anywhere from 100 to 240, which is typical of modern electronics. But here it says 18 VA. Well, VA stands for volt times amps. It's just another way of expressing power in watts. So basically, my battery charger uses 18 watts of power, or 18 watt hours for every hour it's turned on. And finally, I looked at the label on my espresso machine. You might have a coffee maker that you use in your RV. I have an espresso machine. I'm a bit fussy. My espresso machine, if you look in here, you'll find that it uses 1200 watts. It's labeled in watts in this case. If I use it for an hour, it'll use 1200 watt hours. So labels on appliances will tell you how much power they use. This slide shows some examples of how to calculate the watt hours consumed by different appliances. Let's take my laptop, for example, which I showed uses 138 watts when it's running. So if I use my laptop for 3 hours while it's plugged in, it'll use 138 times 3, or 414 watt hours. Similarly, if I decide to charge my camera battery, it takes about 40 minutes to get a full charge. That is 0.667 hours. 40 divided by 60 minutes in an hour. So 18 watts times 0.667 hours is 12 watt hours. Similarly, if I decide I want to have a cup of espresso, sounds like a good idea, usually takes about 6 minutes for my espresso machine to make a cup of coffee. While it's doing that, it's using 1200 watts. 6 minutes is 6 divided by 60, or 1/10 of an hour. So 1200 times 0.1 hours is 120 watts. So these are examples of how you can use how long you run your appliances during a day to calculate how much power you use based on the labeled power consumption of those appliances. Now I'd like to run through a couple of examples of calculating power used over a day. I've got two people here I'm using for these examples. One is the minimalist, who's very careful about power consumed and basically uses as little as possible. The other is a more average person who is a little less concerned and uses quite a bit more power as a consequence. Okay, let's look at my minimalist. The minimalist has all LED lights in the RV and only uses about 10 hours of LED light in a day. That might be two lights run for 5 hours each. Given that LED lights burn about 3 watts maximum, 10 hours of LED light is about 30 watt hours. The minimalist's refrigerator, which draws about 10 watts to keep the propane solenoid open and run the control electronics, is turned off at night. He only runs it during the day, so that's 12 hours at 10 watts, or 120 watt hours. The minimalist uses a Mr. Buddy independent propane heater, doesn't bother with the RV's built-in heater, so that's 0 power for that. Electronics, well, the minimalist does run his laptop for a while, maybe some other electronics, charges the phone, so about 400 watt hours. And then keeps the miscellaneous stuff to a minimum, 100 watt hours. That adds up to 650 watt hours. Now let's go to our average person. Average person's a lot more profligate with the lights, leaves them on in parts of the RV where he's not working, maybe uses 90 watt hours. Maybe has 4 or 5 lights on at a time. Refrigerator just left on all the time, 10 watts an hour for 24 hours, 240 watt hours. Runs the heater for a while, that really sucks up the power, and that might be 200 watt hours. And maybe watches some TV, runs the laptop, listens to music, all these things add up, 600 watt hours. And then on the miscellaneous side, uses a coffee maker, cooks a little bit in the microwave. Microwaves are 1,000 watts, so even running the microwave for 1/10 of an hour is going to be 100 watts, so that adds up quickly. So you're looking at maybe another 500 watt hours. Total 1,630 watt hours. Now, before we go on, we're going to look at converting these watt hours to the units that are used for battery capacity, which is amp hours. So if I divide these watt hours by the average battery voltage while the appliances were on, which might be, say, 12.5 volts, because the batteries are drawn down a little bit by this current, that works out to 52 amp hours for the minimalist, and for my more average person, 131 amp hours. You can see our just a little bit more consumption or a little bit less care can lead to a lot more electrical use that you're going to have to replace with the solar panels. Okay, I'm going to summarize now. The minimalist used about 50 amp hours from the batteries during the day, and the average person 130 amp hours. Batteries are not 100% efficient at charging. Typically they're about 80-81% efficient, so it's going to take more amp hours to recharge the batteries than we took out of the batteries. So the minimalist might need, for example, 60 amp hours, where the average person 155 amp hours. Now, the next column shows batteries. This is minimum battery capacity that these two users need. How did I get to that number? Well, lead acid batteries, which includes flooded batteries, AGM batteries, sealed batteries, gel cell batteries, they're all lead acid batteries, just differences in the way the lead is contained and the acid is contained, really shouldn't be discharged more than about 50%. And less is better. If you discharge them 20%, they'll last a lot longer than they do if you discharge them 50%. And if you discharge them 50%, they'll last longer than they will if you discharge them 75%. But 50% is a kind of rule of thumb for the maximum discharge that should occur. Minimalist really needs about 100 amp hours of battery capacity. That might be one Group 27 battery. Similarly, the average person needs about 260 amp hours of battery capacity. It's a little harder to come by because of the sizes of batteries, but they say 3 Group 27 batteries with a little extra capacity. And that's about the minimum that these two users can get away with. What about solar panel requirements? How much solar panel array is it going to take to produce 60 amp hours of charging capacity or 155 amp hours of charging capacity? Well, solar panels are in watts, not amp hours, so we have to convert from amp hours to watt hours, which is done by multiplying by the charging voltage. When we do that, we come out that the minimalist needs about 750 watt hours to recharge his battery, and the average person requires about 1625 watt hours for recharge. If we look at our Arizona numbers, where we had our shortest day, 9.5 hours, that means the minimalist needs to get about 79 watts per hour out of the solar panels. You might think that that's one 100 watt solar panel, but no, it's going to work out to be more than that. Similarly, the average person needs about 170 watts per hour for the 9.5 hours of the day. Now let's look at how solar panels actually work. A 100 watt solar panel does not put out 100 watts from sunup till sundown. This graph here shows some real data that I borrowed from the Energy Information Agency for solar panel output as a function of time of day. It starts out at 0 at sunrise, goes up to a maximum right around noon, solar noon when we have maximum solar intensity, and then drops off to 0 again at sunset. If we were to compare the area under this curve, which would be the actual output, to the theoretical output for a solar panel that received 9.5 hours of strong sunlight, it would work out that a tilted panel that's facing the sun over the course of a day will produce about 46% of theoretical capacity. So if it was a 10-hour day and a 100 watt panel which had a theoretical capacity of 1,000 watts, it would produce about 460 watts on an average sunny day. If the panel is horizontal, flat, it's going to be a little bit less efficient and might only produce 39%. So I've calculated about how much we can expect in terms of wattage from a 100 watt panel over the course of a day. For a 9.5 hour day in Arizona in the middle of the winter, and for a 14.5 hour day up in the northern United States in, say, early May or late September. That 100 watt panel is going to produce about 435 watt hours over the course of my 9.5 hour day and 667 watt hours over the longer early summer day. The flat panel will produce about 370 watt hours or 565 watt hours for 9.5 or 14.5 hour days respectively. If we now go back to the amount of power that was needed to charge the batteries for the minimalist, that works out to 172 watts of solar panel, which is 750 divided by 435 for the tilted panel, or 202 watts of solar panels for horizontal or flat panels. The average person who uses a lot more power is going to need at least 375 watts of solar if they tilt their panels up toward the sun, and 440 watts of solar panels if they have them flat, say attached to the roof of the RV. Now this is for a sunny day. This is the minimum you can get away with. You probably want to go with more than this to account for cloudy days when solar output will be less. You might think that we've come to a final conclusion about how much solar panel array size is needed for my two users, but there's one other consideration. That's the type of solar panel controller that's being used, or charge controller. Basically there are three types. There's an on-off controller that simply turns on when the battery voltage is low, turns off when the battery voltage gets up to a reasonable state of charge. On-off controllers were the earliest solar charge controllers. They're still available, but basically almost no one uses them anymore. They're not very sophisticated. A more sophisticated and quite common type of controller is called a PWM controller, where PWM stands for pulse width modulation. Basically what these controllers do is adjust the percentage of time that the solar array is connected to the battery by sending little pulses of voltage that are very short. They might be 1/30th of a second long to the batteries, and the off time between pulses determines how much power gets sent to the battery. So if you have a pulse that's 1/30th of a second long, then you're off for 1/10th of a second, and then another pulse, and so on. You'll get less power than if you have 1/30th of a second pulse, off for 1/30th of a second, then on for 1/30th of a second. So by adjusting the width of the pulses, you can adjust how much power is going into the battery from the solar panel. The disadvantage of these controllers is that when the switch is open, when a pulse is going out, the solar panel voltage is directly coupled to the battery voltage, which forces the solar panel output voltage down to the battery voltage. That said, these controllers are quite sophisticated. They have multiple charging stages where they adjust the voltage that's going into the battery and can produce very effective charging. But because they pull down the voltage of the solar panel, the total power put out by the solar panel, which is voltage times watts, is less than the maximum possible for the panel. Now, the final controller type is an MPPT controller, where MPPT stands for Maximum Power Point Tracking. These controllers differ from PWM or on-off controllers in that they decouple the solar panel's operating voltage from battery voltage. They do that by using an electronic circuit called a DC to DC converter. What a DC to DC converter does is it takes in power in the form of volts and amps from one source, and it converts that power into a different voltage level and a different amperage level, but still the same power for output. So you might have a 100-watt solar panel that's running at 18 volts and putting out 5.5 amps. That's basically 100 watts. And the DC to DC converter might convert that down to 14 volts to charge the battery, but at 7 amps, which is also essentially 100 watts. The difference here is, compared to a PWM controller, is that the PWM controller would maybe produce that same 14 charging volts, but at 5.5 amps. So the MPPT controller would produce the 14 volts at 7 amps. That's a pretty significant difference in total power going into charging, and that's the advantage of the MPPT controller, and I'll try to explain that more in the next slide. Okay, these two slides are to illustrate the differences in the way PWM and MPPT controllers operate in terms of power. In the left-hand slide, I've plotted volts against time of day, and the curved part is, it's got MPPT under it, is the voltage of the solar panel as it's operating over the course of a day, with its maximum at noon. The MPPT panel will track the solar panel voltage and allow the solar panel to put out its full voltage throughout the day. The PWM panel, in contrast, might only produce 14.4 volts for bulk charging during the course of the day. So the area, the light colored area under the top curve labeled MPPT, is voltage times amps, that little area that is lost by the PWM panel, that is retained, that the MPPT panel or controller would put out. Now, here's another example of that. I've plotted over here watts output from the solar panel controller array as a function of time of day. The upper curve is the output from the MPPT panel. You can see it's higher, particularly during the brightest period of the day where the solar panel is putting out its highest output, and the PWM panel is putting out a lower output at all times except right at the very beginning and end of the day. So MPPT has an advantage over PWM, particularly during the brightest part of the day around noon, when you're probably getting the most output from your panel. In this particular case, the panel equipped with a PWM controller only puts out about 84% of the amount of charge that the same panel equipped with an MPPT controller would. And I've adjusted this for 95% efficiency for the MPPT controller. So this really illustrates the difference between the two and why the MPPT controller is a better choice for a solar panel. Okay, now let's apply different types of controllers to our panels and our required panel size. Earlier we had concluded that the minimalist needed 172 watts of solar panels if he could tilt the panels to face the sun, or 202 watts of panels if the panels were flat on top of the RV, for example. And our average user needed 375 watts of tiltable panels or 440 watts of flat panels. If we look at the two different controller types, PWM and MPPT, PWM typically is going to be, say, 84% of the output, charging output of an MPPT controller. Now this is for a single panel or multiple panels wired in parallel. The PWM will be even worse compared to multiple panels wired in series. Now this is sort of a worst case scenario for the PWM. Temperature does affect the output of solar panels and will affect the difference between PWM and MPPT controllers. But since we're trying to size the array, we really should use the worst case. So when I consider the different controller types and adjust the panel size requirements, I come out with, if the minimalist uses an MPPT controller, that the solar panel array needs to be 181 watts if the panels can be tilted to face the sun, and 215 watts if the panels are flat. With a PWM controller, the array needs to be 215 watts if the panels can be tilted, and 253 watts if the panels are flat. Similarly, for the average user who uses more power, with the MPPT controller, you need 395 watts of panels if they can be tilted, and 460 watts roughly of panels if they're flat. With the PWM controller, 470 watts if they can be tilted, and 551 watts if they're flat. These differences basically come out to one more 100 watt panel with the PWM controller than with an MPPT controller, which is about another $120 or so, which will pay for the MPPT controller. So you have a choice. Buy an MPPT controller, maybe have a smaller number of panels. That might be an advantage because of the available area to mount panels, or the number of panels you have to wrestle around if you've gone with a portable setup. Or you can go with an MPPT controller have fewer panels to wrestle around or occupy less space on top of your RV. So that's pretty much what I want to say about how do we decide how much solar is needed to run an RV. This is the procedure that you might go through, and these are the major considerations. The next video in this series is going to address the nuts and bolts of setting up the system. What kind of panels to use. We've already gone over what kind of controller, I think MPPT, and what type of batteries are best. And what about inverters to produce AC power for charging things like phones and camera batteries and running laptops? So I'm going to go over all that in the next video in this series, which should be out in a couple of days. Thank you very much for putting up with this long video. I hope you found it useful and got some information out of it that's of value to you, and that you have a better understanding of how to size a solar array for an RV. If you liked it, please click the thumbs up button. If you didn't like it, click thumbs down. Doesn't bother me, but please comment and tell me why. If you want to get notifications, click the subscribe button. Thank you very much.